Okay, this is linear algebra, lecture 8. And I was asked to do on page 75, exercise 6. So we have a matrix, a 2x2 matrix, A, B, C, D. And we have an inhomogeneous system of equations. AX plus BY equals R, and CX plus DY equals S. So we want to prove this system has a unique solution if and only if the determinant of A is non-zero. So if this is the matrix A, the determinant of a matrix, of a 2x2 matrix, is AD minus BC. You take the product of the two numbers on the main diagonal minus the product of the two numbers on the sort of anti-diagonal. So we want to solve this equation. Okay, well, let's see. Suppose we just try and solve it. So I want to solve the inhomogeneous system. So I can cancel the y, for example. I can multiply the first equation by d. I get AD plus BDY equals RD. I can multiply the second equation by b. I get BCX plus BDY equals SB. I can subtract. When I subtract, these terms cancel. I get ADX minus BCX equals RD minus SB. And of course, this, if I factor out the x, is AD minus BC times x. So, and what is AD minus BC? That's the determinant. So, if the determinant of A, which is AD minus BC, is different from 0, then x has to be equal to RD minus B minus SB over this determinant. And there's no choice about that. Similarly, in these equations, if I want to eliminate the x, I can multiply the first equation by c. I get ACX plus BCY equals RC. I can multiply the second equation by D. Sorry, I can multiply the second equation by, there's a Y here. I can multiply the second equation by A. I get ACX plus ADY equals SA. If I subtract the first equation from the second, I get ADY minus BCY equals SA minus RC. And again, if I factor out the y, this is AD minus BC times y, so which is the determinant. So again, if the determinant is not 0, I can divide by this. So y has to be equal to SA minus RC over the determinant of A. So what this says is that if the determinant of A is different from 0, then these equations have a unique solution. So this is half of what we're supposed to prove. If the determinant is different from 0, the equations have a unique solution. And all right, so let me stop for a second. Oh, and I just proved the second part of this also, because if the determinant is non-zero, then x, what is RD minus SB? That's exactly the determinant of the matrix RS BD over the determinant of A. because this 2 by 2 matrix, the determinant is RD minus SB. And similarly, SA minus RC is the determinant of the 2 by 2 matrix ACRS over the determinant of A. Because again, the determinant of this 2 by 2 matrix is SA minus RC. So if the determinant is non-zero, the equations have a unique solution. And in fact, here's a formula for the solution. Okay.
I have a question. On the right-hand side, the ADY minus BCY, that cancels out and leaves you with...
Well, ADY minus B, it doesn't cancel out, but you can factor out the Y. If you factor out the Y, you get AD minus BC times Y, right? So in this expression, here I have a Y and here I have a Y. If I factor it out, I get AD minus BC times Y. And AD minus BC is, by definition, the determinant of the matrix A.
Okay, that's why determinant A is the denominator?
Yeah, right, because this is the determinant of A. So I can divide by it, and Y is equal to this divided by the determinant of A. And this can be seen as the determinant of this particular 2 by 2 matrix.
Okay.
Okay.
I have another question on the homework, just one more.
Yeah, go ahead.
Okay, let me tell you the pages. So, one moment. So I didn't understand very much number 5. It was on page 74 through 76, exercise 5. It begins with the determinant of the 2 by 2 matrix.
Mm-hmm.
A equals A, B, C, D.
Right.
Yeah, there's multiples, there's A, B, and C.
Okay. So let's take a look at that. These are all very nice problems. So this is again on page 75, exercise 5. We have a 2 by 2 matrix A, which is A, B, C, D. And the determinant of A is defined to be AD minus BC. And we want to prove that the column vectors of the matrix are linearly independent if and only if the determinant of A is 0. So what are the column vectors? One is AC and the other is BD. So suppose X times the first vector, column vector, and Y times the second column vector is 0. So if this is the case, then how can we write this? So X times AC is the same as the vector AX, CX. And Y times BD is the vector BY, DY. And if we add them, we get AX plus BY, CX plus DY. So that's the sum of these two vectors. And if that's equal to 0, 0, that's the case if and only if AX plus BY equals 0 and CX plus DY equals 0. And so if a linear combination of these two vectors is 0, then X and Y are solutions of this system of homogeneous equations. And I can actually make this all if and only if. So this linear combination of vectors is 0 if and only if AX plus BY equals 0 and CX plus DY equals 0. So if and only if this set of two equations and two unknowns has only the 0 solution. All right. So So again, just as I did a moment ago, if I have the system of equations ax plus by equals 0, cx plus dy equals 0, if I eliminate the y, I can multiply the first equation by d, a dx plus b dy equals 0. I can multiply the second equation by b, bcx plus b dy equals 0. When I subtract, I get ad minus bcx is equal to 0. So if the determinant of a, which is ad minus bc equals 0, ad minus b is not equal to 0, then from this equation you can cancel ad minus bc and x equals 0. So if the determinant is non-zero, then x has to be 0. And if x has to be 0, y has to be 0. That means that if the determinant of a, which is ad minus bc, is not 0, then these column vectors ac and bd are linearly independent. So this is the first part, which is very important. We're going to show here you have a matrix, and if the determinant is non-zero, the column vectors are linearly independent. So what does linear independent means? It means the only linear combination of vectors that's equal to the 0 vector is the trivial linear combination where x and y are 0. But if you have this linear combination of the column vectors equal to 0, that's exactly equivalent to saying that x and y solve this system of two equations and two unknowns. And if the determinant is different from 0, the only solution of these equations is x equal y equals 0. So that's the proof that if the determinant is non-zero, then these two vectors are linearly independent. But what about the opposite case? Suppose the determinant of a, which is ad minus bc, is equal to 0. Right? Must show that the column vectors are linearly dependent. In other words, which is the same as saying this system of equations has a non-zero solution. So how can we find such a solution? So AD minus BC is 0. How do we find a non-zero solution of these equations? So let's see. So what's a nice way to prove that? Let's just do a kind of an experiment. Right? I'm interested in the equations ax plus by equals 0, cx plus dy equals 0. So suppose, let's just look at a simple case. So if a and c are both 0, then these equations simply become, then what? Then a times 1 plus b times 0 is 0 because a is 0, and c times 1 and d times 0 is 0 because c is 0. So 1, 0 is a solution, and that's a non-zero vector. So we can suppose that A and C are not both 0. So suppose A is different from 0. This just as an experiment, let x equal to 1. Then the first equation would say A1 plus B times Y equals 0. So Y would have to equal, solve for Y, minus A over B. What did we get in the second equation? Cx plus dy, well, C times 1 and D times minus A, minus A over B. What is that? That's C minus AD over B. That's minus AD minus BC over B. Let's suppose that B is different from 0. Okay, so here I have these equations. Suppose B is different from 0. If you let x equal 1, y is minus A over B. If you let x equal 1 and y equals minus A over B, Cx plus dy is equal to this, which is equal to what? This is minus the determinant of A over B, which is 0. So if B is different from 0 and the determinant is 0, then the vector xy equal to x equal to 1 and y equal to minus A over B is a non-zero solution. Does this make sense? Is this clear? If not, let me do it a different way, which is maybe clearer. So, alternate solution. So, forget this. So we have the determinant of A, which is AD minus BC equals 0. And we're looking at the equation AX plus BY equals 0, CX plus DY equals 0. So and I want to show that the vectors AC and BD are linearly dependent. Now, if one of them is 0, they're certainly linearly dependent. Suppose I let xy be equal to minus BA. Right? Let me plug this into these equations. What do I get? So AX plus BY is A times minus B plus B times A. That's minus AB plus AB. That's 0. So this is a solution to the first equation. What about the second equation? CX plus DY is C times minus B plus D times A. That's AD minus BC, and that's equal to 0. So this is a solution, a non-zero solution, unless both A and B are 0, right? But if A and B are 0, then what can I say? If A and B are 0, the first equation is 0 no matter what. So if A and B are 0, then so if A and B are 0, but that is if the vector AB is 0, but the vector CD is not 0, then if I let let me write this as minus DC, then A times minus D plus B times C is 0, because A and B are both 0. And C times minus D plus D times C is minus CD plus CD is also 0. So if A and B are both 0, but C and D are not both 0, we have a non-zero solution. And the only other case is when AB is 0 and CD is 0. But if A, B, C, and D are 0, you can let X and Y be anything at all. So that's a proof of the opposite half of this, that if the determinant is non-zero, then the column vectors are linearly dependent. And a similar kind of argument would show that the row vectors are linearly independent if and only if the determinant is non-zero. So what would the argument, I'm sorry, first, is there a question about this?
Yes, so where it starts off, if, can you explain that row, please?
Right here?
Yeah.
This or somewhere else?
Right there, that's that right there.
So what did we show? This is how we started the problem, that here we have the matrix. And these are the column vectors, AC and BD. So they, a linear combination of them equals the 0 vector, X times the first column, plus Y times the second column is the 0 vector, if and only if X and Y are a solution of these two equations and two unknowns. So we want to show that these equations have a non-zero solution if and only if the determinant is 0. If the determinant is non-zero, then you can solve these equations and you get X and Y must be 0. So if the determinant is non-zero, the columns are linearly independent. We have to show that if the determinant is 0, then the columns are linearly dependent. That is, you can find a solution X, Y to these equations which are not both 0. So I said, suppose there are two cases. In the first case, AB, this vector, is not the 0 vector. So if I let X, Y be equal to this minus BA, that this is a non-zero vector because A and B are not both 0. But if I plug in A equals X, if I plug in X equals minus B and Y equal A into the equations, I get 0 for both. So if AB is different from 0, this is a non-zero solution to these equations. The other case is when AB is equal to 0. Now, if C and D are both 0, then A, B, C, D are 0. It doesn't matter what you pick for X and Y, you have a solution of these equations, so there's a non-zero solution. So we have to consider the case where AB is the 0 vector, but C and D are not. That means minus D, C, that vector is not the 0 vector. And then I plug in X equal minus D, Y equal to C into the equations. I get AX plus BY, A times minus D plus BC. What is that? That's the same as minus AD plus BC, or minus AD minus BC, which is 0. And if I plug these variables into the second equation, I get C minus D C times minus D plus DC. That's minus CD plus CD, that's 0. So in this case also, I have a non-zero solution to my system of equations. And that means that the column vectors are linearly dependent.
I understood everything. I'm a little confused about why isn't negative D and C not equal to zero
So
vector?
this is if. If this is 0 and, if you like, this is non-zero, right? So that we might say there are 3 cases
Okay.
in this proof. In the first case, AB is not 0. In the second case, AB is not 0, and CD is not 0. And in the third case, in the first case, AB is not 0. In the second case, AB is 0, that's the alternative, but CD is different from 0. And in what is really the trivial case, AB is 0 and CD is equal to 0. So these are all possible cases. Either this is not 0 or it is. And if it is, either CD is not 0 or it is 0. So we looked at all 3 cases, and in all 3 cases, we found a non-zero solution to the system of equations.
So you chose negative D and C to not equal zero. That was your choosing.
Well, this is to say CD is different from 0 is the same as saying that minus DC is different from 0. It's exactly the same thing, because these are the numbers I'm going to plug into this equation. I plugged in x equal minus D and y equals C.
Okay.
And then in the second part of the problem, we do the same thing with the row vectors. We have the matrix A, B, C, D. And what are the row vectors of this matrix? AB, the first row, and CD is the second row. And we want to know whether these row vectors are linearly independent. That means when is the case that x times AB plus y times CD is the 0 row vector. So again, that's exactly the same if you add these 2 vectors as AX plus CY equals 0. Sorry, AX, when you add these 2 vectors on the right-hand side, you get AX plus CY, BX plus DY. And to say that's the 0 vector, it's the same as saying that the system of equations AX plus CY equals 0, BX plus DY equals 0. X and Y solve this vector equation if and only if XY solves the system of 2 equations and 2 unknowns. And again, we have to show that if the determinant is non-zero, this has only the trivial solution, x equal y equals 0. And if the determinant is 0, then there's a non-trivial solution. So suppose the determinant of A, which is AD minus BC, is 0. We want to solve these equations. So let's say we multiply the first equation by D, and we multiply the second equation by C, and we subtract, these cancel, we get AD minus BC times X equals 0, and AD minus BC is not 0, so X equals 0, and if X is 0, then Y is 0. So X is 0, CY and DY are both 0, CD isn't equal to 0, because otherwise this would be 0, so Y has to be 0. So if the determinant is non-zero, the row vectors are linearly dependent. Suppose the determinant of A, which is AD minus BC, is equal to 0. If I look at the equations, well, let's see. Suppose I let xy be equal to AD minus BC. Suppose I let xy be equal to d minus b. Then in the first equation, I get ax plus cy is ad plus c times minus b, which is ad minus bc is 0. And in the second equation, I get bd plus d times minus b, which is bd minus bd, is also 0. So if the determinant is 0, then this is a solution of the equations, and it's a non-trivial solution if b and d are not both 0. So the only so if the determinant of A is 0, and also B equal D equals 0, then what do we say?
I have a question.
Yeah, go ahead.
So where it says ADX plus CDY equals 0 and under that as well, how did you form that?
So I have AX plus CY equals 0, okay? If I multiply this equation by D, I get ADX plus CDY equals 0 times D, which is 0. I'm multiplying the first equation by D, and I'm multiplying the second equation by C.
Okay. And then can you explain on the right-hand side of that, I see AD minus BC.
So when you subtract one equation from the other, CDY, CDY, they cancel. So I'm left with ADX minus BCX equals 0. And if I factor out the x, I get AD minus BC times x is 0. But I'm assuming that the determinant is non-zero. If AD minus BC is different from 0, then the only way this is 0 if x is 0. And if x is 0, then in these equations, y has to be 0.
Okay.
So this is sort of a lot of, I don't know, you might just call it high school algebra, but it's so much high school algebra, you couldn't possibly do it in high school, but you do it in linear algebra. So what this says is then the row vectors are linearly independent if and only if the determinant is 0, if and only if the column vectors are linearly independent. So in a 2x2 matrix, the row vectors are linearly independent if and only if the column vectors are linearly independent. Any other questions about anything we've done in the homework or in the text? Now let's look at some of the problems, some problems having to do with matrix multiplication. So this is the next section. And this is a technical skill you absolutely, positively have to master. So in 2 or 3 weeks, you'll have 2 weeks notice, but in the middle of October, we'll have the first midterm, which is in person on campus. And you won't have a computer or a calculator. You'll have to be able to do these operations of matrix addition and multiplication by hand correctly. So let's look at page 82. Exercise number 1. We have A is the matrix 7, 1, 0, minus 2. B is the matrix 8, minus 3, minus 1, 4. So if you had to calculate something like 5A minus 6B, that's 5 times the matrix 7, 1, 0, minus 2, minus 6 times the matrix 8, minus 3, minus 1, 4. When you multiply this matrix by the scalar, by the scalar 5, you multiply every coordinate by 5. 35, 5, 0, minus 10. And when you multiply every coordinate here by 6, you get 48 minus 18 minus 6, 24, if I've done this correctly. 48 minus 18 minus 6, 24. And when you subtract, you get 35 minus 48 minus 13. 5 minus 18 is 5 plus 18 is 23. 0 minus 6 is plus 6. And minus 10 minus 24 is minus 34. So that's the solution. Okay. Any questions about this? Because these are basic manipulations, calculations you have to do. What is A times B? 7, 1, 0, minus 2. 8 minus 3 minus 1, 4. Matrix multiplication is going to be a 2 by 2 matrix. Row into column. 56 minus 1 is 55. Minus 21 plus 4 is minus 17. 0 plus 2 is 2. 0 minus 8 is minus 8. So A times B is this. What happens if you multiply in the opposite order? 8 minus 3 minus 1, 4 times 7, 1, 0 minus 2. 56 minus 0 is 56. 8 plus 6 is 14. Minus 7 plus 0 is minus 7. Minus 1 minus 8 is minus 9. So this is AB and this is BA. And you see that AB is different from BA. This is very important. We say that matrix multiplication is not commutative. The order that you multiply in matters. AB is different from BA. So in particular, yeah, go ahead.
Question. So where you got 55, negative 17, and 2 and negative 8, can you explain that one more time, how you got it?
Okay, so here I want to get the entry in the first row, first column of the product. So I multiply the first row of A times the first column of B. 7 times 8 is 56. 1 times minus 1 is minus 1. 56 minus 1 is 55.
Okay, so you multiply the 7 and the 8, and then you subtract it by what?
I'm multiplying row into column. When you have to know how to multiply a row vector times a column vector. If you can't do that, you can't.
Yeah, but I'm
multiply.
asking a question because I need help. So
No, I'm not saying. So that's why this is important. So you take this row times this column, you multiply the first coordinate of each, and you add the product of the second coordinates of each. The first coordinate is 56, 7 times 8. Second coordinate is -1. 56 minus 1 is 55.
Okay.
All right. If I want to get, how do I get this? This is the coordinate in the first row, second column. So now I'm multiplying the first row of A times the second column of B. So the first coordinate, 7 minus 3, minus 21. Second coordinate's 1, 4, that's 4. Minus 21 plus 4 is minus 17.
Okay.
So really, the most important thing is to know how to multiply a row vector times a column vector. That really is, that's like the fundamental thing, because matrix multiplication just consists of doing that over and over and over again for every coordinate in the product. And if I look, so an AB is different from BA. So if I want to subtract AB minus BA, AB is the matrix 55 minus 17, 2 minus 8, minus BA, which is 56, 14, minus 7, minus 9. You subtract matrices by subtracting coordinates. 55 minus 56 is minus 1. Minus 17 minus 41 is minus 31. 2 minus minus 7 is 2 plus 7 is 9. Minus 8 minus minus 9 is minus 8 plus 9 is 1. So AB minus BA is this matrix. Right. That's just what it turns out to be, and that's it.
Would you be able to do the proof for number 4?
Sorry, for what?
Page 83.
Okay, sure. I mean, they're not really proofs, they're really computations, but it's not the same as proving a theorem. But sure, let me do that. This is, we're up to page 7. Okay, so this is on page 83, exercise 4. So I have, so there's just a lot of calculation here. I have I have 3 matrices. P12 is 0, 1, 0, 1, 0, 0, 0, 0, 1. P13 is 0, 0, 1, 0, 1, 0, 1, 0, 0. And P23 is 1, 0, 0, 0, 0, 1, 0, 1, 0. So I want to square each of these matrices. It's like 3 separate calculations. So what is P12 squared? Squaring a matrix means you multiply it by itself. Just the way squaring a number means you multiply it by itself. So if I take first row into first column, I get 1. If I take the first row into the second column, I get 0. If I take the first row into the third column, I get 0. Okay. If I take the second row into the first column, I get 0. Second row into second column is 1. Second row into third column, again, I'm just doing multiplying row times column, is 0. Third row into the first column is 0. Third row into the second column is 0. Third row into the third column is 1. And this is exactly the 3 by 3 identity matrix, right? That's what I3 means. So, and again, you can similarly, you can square, so I don't have to do it. If I take P13 and square it, or P23 and square it. In those cases, I also get the identity. All right. What about P12 times P13? I want to show two matrices are different, so I have to calculate them. I have to calculate P12, P13, and P13, P12. So P12, P13, this is P12. P13 is this. So I'm multiplying 3 by 3 matrices. I get a 3 by 3 matrix. I multiply the first row into the first column, I get 0. First row into the second column is 1. First row into the third column is 0. First row into the first column is 0. Sorry, second row into the first column is 0. Second row into the second column is 0. Second row into the third column is 1. Third row into the first column is 1. Into the second and third columns gives me 0. So this matrix is P1213. All right? It's just a calculation. What about P1312? So P13 is this matrix. P12 is this matrix. What do I get? First row into the first column is 0. First row into the second column is 0. First row into the third column is 1. Second row into the first column is 1. Second row into the second column is 0. Second row into the third column is 0. First row into the first column is 0. First row into the second column is 1. First row into the third column is 0. And if I look at these two matrices, they're different. So P12, P13 is different from P13, P12. It's just an exercise in matrix multiplication.
Professor, I'm confused. How did you multiply these rows and columns? You took each number?
Well, so
Confused.
if you have a row matrix, let's say it has n numbers in it, A1, A2, A3, up to AN. That's an n-dimensional row vector. And suppose we have an n-dimensional column vector. So this is a column vector with n numbers. The definition of the product is you multiply the first coordinates, you multiply the second coordinates, you multiply the third coordinates, all the way up, and then you multiply the nth coordinates, and then you add up these numbers, right? That's multiplying a row times a column. So for example, if you had 7, 2 minus 1 times 3, 11 minus 9, what would that be? 7 times 3 plus 2 times 11 plus minus 1 times minus 9. First coordinates, second coordinates, third coordinates, and you add. That's 21 plus 22 plus 9. So that is whatever it is, 52, I think. Right? Row into column. That's the definition of multiplying a row by a column, and that's how you do matrix multiplication. Right? And there are a lot of examples worked out completely in the text that you can study from. Let me just keep doing examples since this is something, I mean, there's no way you can pass a course in linear algebra if you can't multiply matrices. Because you do it, you'll be doing it in almost every problem. That's what linear algebra is about, vectors and matrices. Let's look at another one of the problems in this set.
Quick question. For the
Yeah.
midterm, will it be proof heavy?
Well, it won't be proof heavy, but it depends what you mean by a proof. Like in problem 4, that was really a calculation. It wasn't a proof. I could
Well,
say,
like the proof you did before.
excuse me?
like the proof from
So
earlier?
it won't
Not
be
the
proof
one.
heavy, but there will be proofs.
Okay.
Be more calculations by far than proofs. But there will be some elementary proofs.
I have a question.
Yes,
Is the midterm by the board of Lehman?
what do you mean by the board?
Like, is it the same exam for, there's different teachers that teach this course. So
Oh, everyone teaches it differently.
exactly. So I'm just asking if the test is
No,
the
no, no,
same.
it's not, there's not a uniform, there certainly is not a uniform final the way there is in calculus. Every instructor makes up her or his exams.
Okay. And
Right,
for the
so-
final as well.
Sorry?
The final exam as well.
Yeah, right, exactly. And in fact, there aren't very many sections of linear algebra. I don't know how many there are, but maybe there are 2, I'm not sure. But there's no common final in linear algebra. Okay. Even in Calc 3, there's no common final. It's up to each instructor.
What do you mean common final? Or
Excuse
like the
me?
same,
What?
like the same final from
Yeah,
different?
that just means the department makes up an exam. Like in calculus,
Mhm.
the exam is made up by the department. It's not made up by the instructor.
Okay.
And the exams, so everyone's taking essentially the same exam. There are different questions and different numbers but the exam's the same exam. And in fact, we go over the exam, we go over practice exams in calculus before the final. But that's not the case in Calc 3 or any 300 level math class. There's no departmental final. It's each class has its own final.
So are we gonna have like a review for the midterm?
Oh, there'll be a review for each exam and a review for the final. Yeah, absolutely. All right. Let's go back to page 82. Look at number 2. So here we have 2 matrices, 9, -1, 4, and 3, 0, 2, and a matrix D, which is 1, -13, -2, 5, 0, and 8. So you notice these matrices have different shapes. This is a 2 by 3 matrix. 2 rows, 3 columns. This is a 3 by 2 matrix. 3 rows, 2 columns. So you cannot add these matrices. C plus D makes no sense. You only can add matrices that have the same shape. But you can multiply matrices so long as the number of columns in the left matrix equals the number of rows on the right. So I can multiply C times D, because this has 3 columns and this has 3 rows. So this is 9 -1, 4, 3, 0, 2 times 1 -2, 0, -13, 5, 8. So I can multiply row into column. And what's the shape of the final matrix going to be? It's going to be a 2 by 2 matrix, right? 2 rows, 2 columns. How do you get the first row? You multiply the first row, the coordinate in the first row, first column. You take the first row of the matrix on the left times the first column of the matrix on the right, and you multiply them. 9 times 1 is 9. -1 -2 is, you multiply, you get +2. 9 and 2 is 11. 4 times 0 is 0. This is 11, right? All right, let me just make this sort of clear. 9 -1, 4, this column, times 1 -2, 0 is 11, right? That's where this 11 comes from. One entry goes in the first row, second column. I take the first row times the second column. 9 times -13 is -117. minus 1 times 5 is minus 5. So if I were when I multiply 9 minus 1, 4, this first row, times the second column, minus 13, 5, 8. What is that? That's 9 times minus 13 plus minus 1 times 5 plus 4 times 8. That's minus 117 minus 5 plus 32. So that's minus 122 plus 32. So I think that's minus 90.
It's 90. Yeah.
Second row, first column, this row times this row is 3 plus 0 plus 0. Second row, second column is minus 3 times 39, is 3 times minus 13. That's minus 39 plus 0 plus 16. Minus 39 plus 16, I think, is minus 23. So if I did my arithmetic correctly, when I multiply this matrix by this matrix, I get this 2 by 2 matrix. So you should check my calculations to see if I did it correctly. There's a 50-50 chance that I did.
Can we do DC?
Let me finish. Sorry, DC, yes. So what about DC? So D is the matrix 1 minus 2, 0, minus 13, 5, 8. So this is a 3 by 2 matrix. And I'm multiplying it by C, 9 minus 1, 4, 3, 0, 2, which is a 2 by 3 matrix. And the product is going to be a 3 by 3 matrix, right? CD was a 2 by 2 matrix. DC is a 3 by 3 matrix. What goes in the first row, first column? Take the first row times the first column. 9 minus 39 is minus 30. First row, second column. Minus 1 plus 0 is minus 1. Third row, first column. First row, third column. First row, third column. 4 minus 26 is minus 22. Second row, first column. Second row, first column. Minus 18 plus 15 is minus 3. Second row, second column. 2 plus 0. Second row, third column. Minus 8 plus 10. Third row, first column. 0 plus 24. Third row, second column, 0 plus 0. Third row, third column, 0 plus 16. So DC is this 3 by 3 matrix. Okay. And again, you can see the product CD is defined, the product DC is defined, but they're completely different shaped matrices. 2 by 2, 3 by 3. That's what it is. Okay. So it's useful going over problems. Any other questions that anyone would like me to do?
Wait, how you got -1?
Right here?
Yeah.
Let's see, first row. So this is the first row, second column entry. So here's the first row of D. Here's the second column of C. So when I multiply 1
Times
minus 13 times -1, 0, that's 1 times -1 minus 13 times 0 is -1.
I see. One, two. Can we do number 3?
On that same set?
Yeah, the next problem.
So that's page 10. So this is on pages 82, 83. Number 3, we have a 2 by 2 matrix, 1, 2, 3 minus 1. And we want to calculate powers of the matrix. So A squared means A times A. So 1, 2, 3 minus 1 times 1, 2, 3 minus 1. That's 1 plus 6 is 7. 2 minus 2 is 0. 3 minus 3 is 0. 6 plus 1 is 7. Okay. 1, 2, 3 minus 1. 7, 0, 0, 1. Okay. That's A squared. A cubed means A times A times A. But that's the same as, for example, A
squared times
A squared. So
Yeah.
A is 1, 2, 3 minus 1, and A squared is 7, 0, 0, 7. So when I multiply, I get 7 plus 0, 0, 14, 21, 0, minus 7. That's A cubed. A fourth, again, this is A times A times A times A. I could write that as A times A cubed, though it's even actually easier to write this as A squared times A squared, because A squared is so simple. Then this is 7007, 7007. When I multiply this, I get 49, 0, 0, 49. Right? That's A to the fourth. And you continue. A to the fifth is A times A to the fourth. A to the sixth you could write as A squared times A to the fourth. And you calculate them the same way. Right? That's part A. In part B, we have a polynomial P of x equals 2x squared minus x plus 5. So you know how to evaluate a polynomial when x is a number, right? Like if you put in x equals 0, you would get 5. But you can also evaluate a polynomial at a matrix. So what is P of A? This is going to mean, this means 2a squared minus a plus 5 times the identity matrix. That's how you insert a polynomial into, well, that's how you insert a matrix into a polynomial. So a squared we calculated, that's 27007 minus a 1, 2, 3 minus 1 plus 5 times the identity. And now we just do this calculation. 5 times this, sorry, 2 times this is 140014 minus 1, 2, 3 minus 1 plus 5 times this, 5005. So when you add these matrices up, 14 minus 1 is 13 plus 5 is 23. 0 minus 2 plus 0 is minus 2. 0 minus 3 plus 0 is minus 3. 14 plus 3 is 17. Plus 5 is 22. I mean, you do the calculation and you get the answer.
Where you replace the X with the A?
Yes, that's what I mean. And 5 times this is 5 is the same as 5 times 1, which you can think of as x to the 0. And but that's just when you plug in a to the 0, the matrix a to the 0th power is the identity. Just the way the 0th power of a number is 1, the 0th power of a matrix is the identity matrix. Okay. Let me just review one other operation on a matrix, which is called the transpose of a matrix. So for example, if A is the matrix 1, 2, 3, 4, 5, 6, a transpose, which we write by adding this superscript T, you just turn the rows into columns and the columns into rows. So in this matrix, the first row is 1, 2, 3. So in the transpose, the first column is 1, 2, 3. Here, the second row is 4, 5, 6. So here, the second column is 4, 5, 6. Right. That's the transpose of a matrix. And you can also take the transpose of a vector. A vector is just a matrix with one row or column. So if you had the vector 1, 2, 3, then the transpose VT is 1, 2, 3. Right? And if you had vectors x equal to a column vector, say 1, 2, 3, then x transpose, this column becomes a row, 1, 2, 3. Right? Right, the operation of taking a transpose changes rows into columns and columns into rows. So if this is x transpose. And suppose y were the column vector 4, 5, 6. So you can multiply a row times a vector. Here's x is a column, but x transpose is a row. So x transpose y, if I have two column vectors, x and y, I can define x transpose y as a row times a vector. This is 1, 2, 3 times 4, 5, 6. So by the rule for multiplying a row times a column, this is 1 times 4 plus 2 times 5 plus 3 times 6. 14 plus 18 is, I think, 32. Right? So we'll see the transpose a lot later, but it's important to get used to seeing it. All right. So this is just a simple operation on matrices and vectors. You interchange rows and columns. That's the whole thing. The other important thing we did last week was look at the augmented matrix associated with the system of linear equations. So let's just start with an example. Suppose we have the system of equations x plus 2y equals 5, 3x plus 4y equals 6. So associated with this is the matrix of coefficients of these equations. You look at the x's and the y's, the coefficients are 1, 2, 3, 4. So that's the coefficient matrix. But the augmented matrix you take this matrix 1, 2, 3, 4, and you augment or add to it by adding the right-hand side as a new column. So this is the augmented matrix of the system. All right. And if you want to use Gaussian elimination to solve a system of equations, that corresponds to performing certain row operations on the matrix. What are the elementary row operations on a matrix? There are 3 of them. You can interchange rows. You can multiply a row by a non-zero scalar. And you can add a multiple of one row to another row. And the idea is to form these operations in such a way that you want to put your matrix into what is called reduced row echelon form. And in that case, in each row, the first non-zero number will be a 1. As you any row which is all zeros is at the bottom. And as you go from one row to the next, the first non-zero 1 has moved to the right. And above those initial 1s in each row, above and below, you only have zeros. So if I want to, for example, put this matrix in reduced row echelon form, I have 1, 2, 5. And so this starts with a 1, so I don't need to change the first row. But I want to get a 0 here. So I can take the second row and subtract 3 times the first row. So 3 minus 3 is 0. 4 minus 6 is minus 2. 6 minus 10 is minus 4. So the way I got from this matrix to this matrix is to add minus 3 times the first row to the second row. So now the first row starts with a 1, and everything else in that first column is 0. I want the next row to start with a 1. So I can take the second row and multiply by minus a half. All right. 1, 1, 2, 5. Multiply by minus a half, or same thing as divide by minus 2, I get 0, 1, 2. So now my second row starts with the 1, and this 1 is to the right of the 1 in the first row. But I want everything else in this column to be 0. I have to eliminate this too. So I'm going to key fix the second row and take the first row minus twice the second. 1 minus 0 is 1. 2 minus 2 is 0. 5 minus 4 is 1. So by performing elementary row operations, I transform this matrix into this matrix. And the corresponding systems of equations are equivalent. They have the same solutions. So this matrix corresponded to these equations. This matrix corresponds to the system. Oops, let's see, something's not right, so I have to double check what I did. So I had 1, 2, 5, 3, 4, 6. First row is 1, 2, 5. Second row minus 3 times the first row is 0 minus 2 minus 4. Multiply this row by minus a half. 1, 2, 5, 0, 1, 2. Add minus 2 times the second row to the first row. 0, 1, yeah. So according to this, I get, this is the system of equations. X equal 1, y equals 2. But that is definitely not right. Because if I plug these values into the initial system of equations, it solves the first equation, but not the second. So I have to find out where I made a mistake. Right? So making mistakes is good, really, because it forces you to check work carefully. 1, 2, 5, 3, 4, 6. 3 minus 3 is 0. 4 minus 6. Ah, here's my mistake. Good. 3 minus 3 is 0. 3 plus minus 3 is 0. 4 plus minus 6 is minus 2. 6 plus minus 15, this is a minus 9. That should be minus 9. So if I multiply through by minus a half, this becomes 9 halves. Right? And then when I take the first row minus twice the second, I get 2 minus 2. 5 minus 9 is minus 4. So if this is correct, the solution should be x equals minus 4, y equals 9 halves. So let me check if this is correct. If I plug into the first equation, x plus 2y, I get minus 4 plus 2 times 9 halves is minus 4 plus 9 is 5. That checks. And in my second equation, 3x plus 4y, this is 3 times minus 4 plus 4 times 9 halves. This is minus 12 plus 18, and that is 6. So that's correct too. So it worked out. So again, this method of solving a system of linear equations by writing the augmented matrix using elementary row operations to put the matrix into reduced row echelon form is a fundamental thing in the class that you have to learn. And it is 100% certain there will be a problem using this method to solve equations on the midterm and on the final. This is really sort of basic to what one does. Okay. All right. I sent out an email to say that there are going to be problem sessions every day for the rest of the week. Tonight at 7 o'clock, Thursday at 7 o'clock, and Friday afternoon at 4:30. So if you have questions about matrix multiplication or augmented matrices and anything whatsoever, I strongly encourage you to log on and ask questions. And happy to do that as long as there are questions, and if there are no questions, I go off and eat dinner. Okay. Any questions before we break for the day? Okay, all. Looks like a nice day. Enjoy the day and enjoy the weekend. Next class is next Monday. Bye, all.